Okay, so in this movie clip, let's begin with the concept of access carrier concentrations. So herein, the ends of knot, piece of knot are denoted. So previously, when we are learning the mass action law, how many electrons and how many holes are available in intrinsic pure silicon material, the total number of electrons and total number of holes, that those are two multiplications should be equal to the n sub I square, which is 10 to the 10 square, so total 10 to the 20. So whenever we are talking about this mass action law, actually these are the number of electrons and holes are measured and obtained at thermal equilibrium state, okay, without any externally applied electric field and bias or voltage. These two concepts, electron concentration and hole concentration, those two concentrations are evaluated. Okay, so to explicitly indicate this n has been obtained at thermal equilibrium, from now on, let's use this term naught. Okay, so N naught and P naught, those are two indicates the electron concentration at thermal equilibrium and hole concentration at thermal equilibrium. Okay. Then now, without naught, okay, this N indicates the electron concentration at non-equilibrium state. So we have previously talked about the details, the concept of thermal equilibrium. Okay. So thermal equilibrium means no external force applied. But non-thermal equilibrium state means, a certain amount of voltage has been applied to your silicon sample. Okay, so this N and this N naught should be different, so that the difference between N and N naught indicates what? Yeah, delta N, or access carrier concentrations. Okay, so access means more than the equilibrium state. How many additional electrons are created with respect to the reference number? In this case, reference number should be and not. Okay. Okay. So in that sense, you may estimate and you may write down the equation for excess electrons. Okay. So delta n indicates n minus n naught. So how much additional, how much delta n means these are two difference. So n naught is a reference number. So at thermal equilibrium, this amount of electrons are available, but with the help of externally applied voltage, the total number of electron increases. So this number difference has been described as a delta n. Okay. So similarly, you may complete the equation for excess hole concentrations. Delta P is defined as P minus P naught. Okay. And on the right, on the bottom side, you can see that charge neutrality condition should be satisfied in your sample, right? Therefore, the total number of excess electrons should be well balanced with the total number of excess hole concentrations. So this delta n should be well balanced with delta p, okay, because of charge neutrality condition. And now let's move on to the next concept, low-level injection. This is very, very significant and key concept when understanding Pn Junction Diode, which is biased. Okay. In other words, in your microelectronic circuit, which includes a few Pn Junction diode, why diode can flow current in one direction, not in the other direction. In undergraduate class, you may have a chance to learn Pn Junction diode is, working as a rectifier. In Korean, 정유기. What does 정유기, rectifier, mean? it can direct the current flow in a circuit. Okay, so what is the main physical origin of this directing function? So directing means, 정리하다, 교통 정리하다. In intersection, a police officer is directing the traffic. That means 교통경찰관이 교통을 정리할 때. Okay? Anyhow, sorry about using Korean. For international student, if a police officer is standing up at the intersection, then he or she is, directing and rearranging how the car has been moved and cross over the intersection. Then we can say that the police officer is now currently directing the traffic flow. So same concept can be found in a Pn junction diode. For a certain amount of bias or voltage applied to the Pn junction diode, how the electrons and holes are flowing throughout the Pn junction. What is the main, rule and physics behind it? That key idea can be found from this concept, low-level injection. Okay, so this is a very significant concept in understanding Pn junction diode operational principle. So let me read the sentence that I have brought from your textbook. Quite often, the disturbance, simply speaking, any variation, modification from equilibrium, okay? So non-equilibrium, the amount of non-equilibrium, if we can measure it, is very small, okay? So if this disturbance away from the equilibrium is very small, for example, such that majority carrier concentration is not affected significantly. But, however, minority carrier concentration can be significantly affected. Then we can say that this event is quite equivalent to low-level injection. So in the end, we are going to understand this word, injection, because in the end, we are going to study Pn junction diode. So many holes are injected toward the N-type material. So from the perspective of N-type material, the hole is now injected into its material. Okay. So in this case, this N-type material, majority carrier is electron, as we have learned. If doping concentration for this N-type material is 10 to the 18, then total electron concentration is 10 to the 18. That is equal to the N naught. So suppose that there is a plus voltage applied onto the p-type. Then electric field is formed from p to n side. So hole, positively charged particle. So it is drifted toward the n side. So from the perspective of n side, this hole has been injected into the n-type material. Because of what? Because of this externally applied voltage. So previously, Pn junction diode is at thermal equilibrium. In other words, no voltage. But once voltage, non-zero voltage, say 1 volt, has been applied across this Pn junction diode, then this Pn junction diode is not at thermal equilibrium. But in terms of the total number of free electrons in N-type material, I mean the N, should be equal to the N naught. No matter what, the hole has been injected into the N-type material. Because the number of holes injected into the N-type is too small, is negligible. Okay? So disturbance has been happened, right, to this N-side material. In this N-type material, the non-zero voltage has been applied. So a disturbance has been happened. But if this disturbance is very small, how small it is? Yeah, see here. The majority carrier concentration has not been affected, has not been changed at all because of this injected hole. Because the total number of holes injected into N side is too small. small. Okay, so inside the majority carrier concentration, in this case, N, right? N is not affected significant, not affected a lot. So we can say that N is almost equal to N naught, which is equal to donor's concentration that in this specification 10 to the 18 per cubic centimeter. Okay. However, in Pn junction diode, the hole in the N side, which is a minority carrier, right? So hole concentration P naught, well, we can estimate it using mass section law, right? And this N naught is ND, Ni square. So this P naught, if we plug in the 10 to the 18 in this specific case, that is simply 10 to the 2 per cubic centimeter. Only 100 holes are available per cubic centimeter. But once positive bias has been applied onto this P side, then in this P side, the hole concentration, which is minority carrier, right? Hole concentration can be significantly affected. In other words, this number 100, only 10 to the 2 100 holes are available, but many holes are injected now into the N side because of this plus voltage. So from the perspective of minority carrier concentration, these N side materials, minority carrier concentration can be significantly affected. So in other words, P and P naught is not anymore equal. In other words, P should be much higher than P naught because many holes here are injected into the N side. Okay, so let's read out those sub-bullet. For anti-material, this anti-material here, the variation of hole and the variation of electron should be identical balanced because of charge neutrality condition. This is always true. But this excess carrier concentration number, excess hole concentration, excess electron concentration should be much smaller than the majority carrier concentration. In other words, the total number of holes injected into N side is very small in terms of N naught. But in terms of P naught, the total amount of holes injected into the N side is too much. So the P is much higher than P naught. Okay. Again, in this N side material, the total number of majority carriers is not changed at all because the total number of holes injected into the P from P side to N side is too small. So this hole would not affect the number of electrons in N side. So N is equal to N naught. However, the minority carrier concentration P naught has been changed a lot because of what? Because of the hole injected from P side into the N side. So this P is much higher than P naught, but P minus P naught is defined as delta P, which is equal to the delta N. Okay, but because of charge neutrality condition, this equation is still valid. Okay, so for an anti-material, majority carrier concentration is not affected a lot. In other words, non-equilibrium electron concentration is equal to the equilibrium state electron concentration, but P is not equal to the P naught. Okay, in other words, definitely P is must be much higher than P naught. Okay, but take a look at here. The variation of hole concentration, in other words, delta P, and the variation of electron concentration, delta N, those two are same. And this value is much smaller than what? Yes, N naught. the n-side majority carrier concentration. What if this n minus n naught or delta n is much higher than n naught? In other words, this delta n is equal to delta p, so delta p or delta n means how many holes are injected toward the n side. But this total number of holes injected into the n side is much higher than n naught. So suppose that is 10 to the 18, and the number of holes injected into the n side is 10 to the 20 in this case. Then this majority carrier concentration would also be changed. Then we can say that instead of low level injection, that is high level injection. Okay. So before injection or after injection, the majority carrier concentration is not affected a lot, then we can say that this injection is low level. Okay. However, before and after the injection, the majority carrier concentration is affected a lot, then this injection is high level. Going back to the PN junction diode, under forward bias, you may know this word, forward bias, in Korean, 순방향. So positive bias is applied on the P side and negative bias is applied on the N side, or voltage difference between P and N is positive, then forward bias is applied across the PN junction diode. Then how strong the voltage difference across the PN diode is. If that forward bias voltage is too high, then PN junction diode would experience high level injection. But most likely in microelectronic circuit, the circuit designer would design his or her own circuit design to keep the PN junction diode under low level injection. Okay, in other words, forward bias, the amount of forward bias is very identical to built-in potential or smaller than that. One student has came by my office and she has asked me a question. What if a forward bias voltage is too much? Then what is the final, shape of energy band diagram across PN junction diode? Which is a very nice, great question. So please do that. Try to draw the energy band diagram under forward bias, which is very strong. Say forward bias voltage is 2 times higher than the built-in potential of PN junction diode. What is the final, band diagram shape? Think about this issue. Then that would be a very good question. How deep your understanding on the PN junction diode is. Okay, please do that. I guess because you are a graduate student, so you have some chance to learn the basics and operational principle of PN junction diode. So you may have a chance to draw the energy band diagram under forward bias. But at this time, draw the energy band diagram when the forward bias voltage is 2 times higher than the built-in potential, then what is your own energy band diagram for PN junction diode? That is very kind of a tricky question, but very good question for you to understand the physics of PN junction diode. Okay, so in this movie clip now we are studying the excess carrier concentration, delta and delta P stuff. Afterwards, we have learned the low-level injection, right? So minority carrier concentration has significantly affected a lot, but the majority carrier concentration is never affected significantly. Okay, then now, combining the contents that we have learned in the first movie clip for week 9, let's go over the indirect recombination rate. So from now on, we're gonna study and investigate the recombination rate in the unit of number per second. So every second, how many recombination can be happened in your silicon device? So for that purpose, let's estimate the recombination rate first. But here in indirect recombination means, in silicon material is an indirect band gap material. So indirect recombination means not band to band, but with the help of recombination generation center, you know, at the mid gap, how fast and how slow the recombination processes occurred in silicon material. So let's derive the equations for that. So let's suppose that excess carriers are introduced into the n-type silicon material. So for a given temperature, n-type silicon sample is at thermal equilibrium. So you may guess and you may estimate quantitatively the the total number of electrons and holes at thermal equilibrium. But herein, excess carriers, right? Not its own, but excess carriers out of the n-type silicon material has been introduced, in other words, injected into this n-type silicon material at time t of 0. Then the question is, how does P means a minority carrier concentration in this n-type silicon material, vary over time t, over 0 second, right? So how those holes are recombined in an n-type silicon sample. So let's estimate it. So step number 1 is let's consider the rate of hole concentration, hole recombination via traps. Okay. So previously I said a silicon recombination process in silicon material is dominantly governed by RG centers. Okay, so RG center is named as a trap because it is capturing the free electrons or holes. So it is named as trap. So rate of hole concentration via trap. So let's consider this rate, how to calculate it and how to express it mathematically. So hole concentration means P, but are we talking about the P naught or P? Yeah, P, because now excess carriers are injected into this anti-material. So P naught, we are not talking we are not talking about P naught. We talked about P. So P is varied over time. So dP over dt or round P or over round T in terms of recombination is proportional to what? Proportional to what? Yeah, how many holes are available there? Okay, then it's coefficient of this equation, round P, round T. How many holes are available depending on how many holes are left? The decaying rate would be determined. So it is proportional to how many holes are still left behind. Okay. Then what is a coefficient of this relationship? How the holes are annihilated or killed by electrons. Yeah, through the trap, right? So if the total number of trap is very many, then this decaying process would be happened at a fast rate, right? So round P round T is proportional to is how many holes are available and how many traps are left behind. Okay, and some more, right? So this more has been combined into single term named as CP. So CP P means a hole and C means a capture. So that is then cross-sectional capture coefficient. So cross-sectional coefficient for hole, denoted as CP, has been included in this equation. And one more thing is minus sign. Why minus? Because the hole is combined with electrons. The number of holes are decreasing. So minus is necessary. Okay, we almost done. So in step 1, the rate of hole recombination throughout the traps recombination generation centers in silicon material can be mathematically written as follows. Okay, now let's move on to the next step. Step number 2. Now, under low-level injection conditions, so previously in this question, access carriers are introduced, but herein the author did not specify how much access carriers are introduced into the n-type silicon material. But here the author has assumed that low-level injection is happened. Then the whole generation rate is not significantly affected. So let's try to understand this point. Here is an n-type silicon sample. So at room temperature or at thermal equilibrium, electron holes are available. But previously I mentioned that I put a lot of emphasis on this situation. This electron has never been alive forever. At some point, this electron would be recombined with hole, and at the other place, new electron hole pairs would be created, so that the total number of electrons has not been modified at all. This is named as dynamic situation. In other words, under low-level injection conditions, still the electron hole pairs are dynamically created and removed. But in terms of total number of electrons and holes in this n-type material, there is no change. But in terms of electron concentration, electron hole, you know, for this specific electron and specific hole, those two carriers, electron holes, would never been alive in this n-type silicon material, because this electron and holes are dynamically alive, I would say. So hole generation rate, I mean that this whole this whole generation rate is not significantly affected. What kind of holes are injected into this anti-material, this hole within this anti-material is still generating, still recombining, still generating. Okay, so round P, round T, because this author has asked us how the hole concentration varying. So in step number 1, we focused on how the hole is removed and annihilated throughout the recombination process. But in step number 2, how the holes are generated. Okay, so we should write down the equation for round P, round T with respect to generation. But this value is almost identical to this value. I mean the G equilibrium. Before holes are injecting into n-type, still the holes are generating. Even though holes are now injected into this n-type material, the generating rate would not be affected significantly, right? So that's the reason why I should write down this equation. Round P, round T, G is equal to round P, round T, G equilibrium. Because this generation rate is not affected by these access carriers. Okay? Now, this equation can make our life much, much easier. Because at equilibrium state, generation is happened. Then, on the other side, recombination has always been happened. So round P, round T, G equilibrium plus round P, round T at recombination at equilibrium should be well balanced. So we can write down this guy minus round P, round T are at equilibrium. But in step number 1, what if this is R equivalent? Then this P would be P naught. Same, processing derivation step would be valid. Okay, so round P, round T are at equilibrium is proportional to the how many holes at equilibrium available, and it is also dynamically affected by the number of traps and cross-sectional capture coefficient. So plug in here. Let's leave minus here as it is, and this value is equal to minus Cp NT and P naught. But this minus would be cancelled out with this minus symbol, so in the end we're gonna get this equation. All right, so now round P round T at generation, let's remove all the note here, is described as a function of hole concentration at thermal equilibrium, and round P round TR is proportional to this. Now let's move on. With that in mind, now let's move on to the step number 3 here. Now let's calculate and estimate the net rate of change in P. Okay, in other words, round P round T by recombination as well as generation, then we can simply add them up. Okay, and bring the equation from step number 1 and step number 2 for each, then you're gonna get this equation. Now Cp and T, those two terms are common. So let's rearrange the terms and we're gonna end up with this equation. Okay, but now let's take a look at this guy. P minus P naught, what is it? Yes, excess hole concentration, delta P. Okay, and what is this guy? Just leave out the minus sign here. Cp times Nt. So 1 over Cp times Nt is defined as tau P. Then we can write down this. Later on, this is a lifetime of hole. So if you do some math work to derive the unit for tau P, in other words, 1 over Cp times Nt, then you're going to get the second. Okay, so take a look at the conclusion. In N-type silicon material, a bunch of holes are now injected into this N-type silicon material. Then that injected holes should be recombining with electrons in N-type because N-type has a bunch of electrons. Then the question is how the hole concentration in this N-type material has been varying. The answer, round P round T by R and G is minus delta P over tau P. In other words, delta P. How much holes? Originally, N-type material has its own hole, but hole has now injected into this N-type material. So hole P minus P naught. So this value, how much excess hole concentration can be obtained? This point, delta P, would determine how fast the holes are recombined with electrons in N-type material. Okay, so round P round T by Rg is minus delta P divided by tau P. So here tau P means lifetime. If whole lifetime is very long, this recombination rate would be slow and slow. In other words, the total time elapsed of holes which is injected into the N-type material would live longer because its lifetime is long enough. Okay, even though there are a bunch of electrons in N-type material, the holes injected into the N-type material can still be alive for a certain long time. Okay, so now you may guess, aha, this concept would be very effective when we are learning the Pn junction diode. So if this forward bias to Pn junction diode or plus bias has been applied onto this P side, then the hole in P side would be diffused into the N side because of doping concentration gradient, and as well as the electric field is formed. So once hole is diffused into the N side, and if hole is arrived at in this side, and the electric field would help to drift these holes toward the end of PN junction diode. And this hole drift and diffusion, those are two mechanisms would cause the current flow across the PN junction diode. However, one more thing, here many electrons are available in this antimaterial and holes are now moving toward the end of the N side. And what would be happened between two carriers, electrons and holes? Yeah, following this rule, round P round T by RNG would be affected by how many holes are injected. If injected hole is much higher than P naught, then this recombination generation rate, or most likely recombination rate, would be determined by excess carrier concentration as well as lifetime. Okay, and this lifetime is governed by n sub t, trap concentration. So in this silicon material, how many traps are included? That would determine the lifetime of minority carrier in n-side material. Okay, so many things are interconnected, hooked up together. So defect density, n sub t, or trap density, lifetime, and how fast the minority carrier concentration can be degraded and decreases. That is associated with the recombination generation rate and so on. Okay, so in PN junction diode, drift current, diffusion current, and recombination generation current. So those are three different current components would uh, would become the total current of PN junction diode. So if you have any chance to measure the diode current, then the total amount of current that you measured, it has consist of three different components: drift current, diffusion current, and recombination generation current. All right, so uh, that's for the indirect recombination rate stuff. And now let's move on to the next slide, relaxation to equilibrium state. Well, actually, I have already explained this concept. In PN diode, the hole has now injected into N side, and this hole would recombine with the electron. Then, this N side would, kind of would prefer to become at thermal equilibrium state. Now this positive bias has perturbed the equilibrium state. Okay, because many holes are now injecting into N side, but this electron would cancel out the injected holes so that it is would like to move toward the electric equilibrium state. So we can say that this is, N-side material is trying to be relaxed back to equilibrium state. Okay. So now let's take a look at some sentences here that I have brought from the textbook. Consider a semiconductor with no current flow, okay, in which thermal equilibrium is disturbed. Okay, the thermal equilibrium is not anymore valid by a sudden creation of excess holes and electrons. Maybe this silicon material, a semiconductor, would receive a certain amount of light, so many electron holes are created at a certain position. Then, total number of electrons and holes are away from the thermal equilibrium value. So, sudden creation of excess holes and creation would disturb the total number of electrons and holes. And then, once this light has turned off, then many electron holes created by this light would be annihilated with another electron and holes originally existing in this N-side material. Okay, then we can say that this N-side semiconductor or this system will relax back to its own equilibrium state. By what? Yeah, by the recombination generation mechanisms. Okay, so in antimaterial, the holes suddenly created excess holes would be decaying toward the P naught value. Okay, so P value would asymptotically approaching toward equilibrium hole concentration, but this process would be governed by recombination generation. So as we have learned, this non-equilibrium hole concentration is proportional to the delta P, and the coefficient is lifetime, each lifetime. So depending on by this first order derivative equation, how the excess holes are annihilated with electrons in antimaterial. Okay, so similarly, you can do the same job for the how the minority carrier electrons in antimaterial can be annihilated with holes in a p-type material, and by this rate, round n, round t is proportional to the delta n. Okay. Okay, so now in this slide, let me briefly introduce the concept of lifetime. Well, although I have already explained the concept of lifetime, but let's briefly talk about some more contents of the minority carrier's lifetime. Here, minority carrier lifetime denoted as tau is, definition is average time. Why average? Because there are tons of tremendous amount of electrons and holes available in semiconductors. So we cannot specify the lifetime of a single electron. We should sum them up and average out the lifetime of all the electrons and holes. So we can say that this is minority carrier lifetime is average time. Okay, average time. Excess minority carrier survives. Okay, in a sea of majority carriers. So there are a tremendous number of electrons, and suppose that a single hole are now injected into this sea of major electron carrier into a sea of electrons. What would be happened? Many electrons would prefer to combine with the hole. Okay, then before recombining with the hole, how many seconds the injected hole can survive in the sea of electrons. Okay, so in that concept, you may understand the lifetime. In crystalline silicon material, the lifetime ranges from 1 nanosecond to 1 millisecond. The average time is 1 microsecond. So suppose that for a given silicon material, this is an n-type silicon material, so many electrons available depending on the donor's concentration, right? And the hole has been injected, a single hole has been injected into this n-type silicon material. Question is, how long the hole, injected hole, can survive into the sea of electrons? The answer is, well, on average, 1 microsecond. In other words, it takes 1 microsecond for the injected holes to be recombined with electrons in silicon. Okay, but this tau value, lifetime, is very dependent of what? The density of metallic impurities. In other words, contaminants, and the density of crystalline defects, trap density, N sub T, remember this word? Okay, so depending on the metallic impurities and the density of crystalline defects, those kind of stuff would affect the lifetime. And here in one more concept, deep trap. The opposite word of deep trap is shallow trap. What is the main examples of shallow trap in silicon? Yes, donors and acceptors. Those two guys, donors and acceptors, are the main representative shallow traps. Why shallow traps? Go back to the energy band diagram. Donors' energy states are created near to the conduction band edges. So near to the conduction band edge, donor's energy state has been created. Going back to the week number 1 or number 2, 3, 4, maybe when we have done the doping itself. By injecting donors instead of silicon, if arsenide or phosphorus has replaced the silicon atom, then arsenide phosphorus has five outermost electrons. So the fifth outermost electron would not form the covalent bond with the four neighboring silicon atoms, so that the fifth electron would become free at room temperature. In other words, the fifth electrons would uh, it is very easy in terms of energy difference for the fifth electron of phosphorus or arsenide, such as donor, uh, to become free. In other words, this energy difference, EC minus ED, or ionization energy that we have learned, is very small, just a few 50 millielectron volt compared against the band gap energy, 1.12 electron volt. So the electron is easy to be released out. Now you may guess or capture the concept of shallow. Easy to become free. Easy means this trap site is very shallow, so once you're trapped in other words, it is also easy to trap out, right? In and out process is very easy. So whenever we are talking about something is easy means the energy difference is very small. Then the electrons can get in and get out very simple without too much uh, variation of energy. But if energy state created at the mid gap, it is not easy to get in and out to this trap site. Then we can say that this trap is deep trap. So once electron or holes are captured into this deep trap, it is not easy to get out and get in. Why? At least to get in and get out, half band gap energy should be required. Okay? So this deep trap can become the recombination generation centers, because the recombination generation is always associated with a huge amount of energy. Why huge? Donors and acceptors ionization energy is just a few tens of millielectron volt, which is about 1% of 1 to 5% of band gap energy. But when we are talking about the recombination generation process, it is always associated with the deep traps. In other words, band-to-band generation, band-to-band recombination, or RG center recombination, RG center generation, those stuff, how much energy variation has been associated related to this process. Yeah, much higher than a few tens of millielectron volt, much higher than the ionization energy of donors and acceptors. That's the main reason why we're saying that this is a deep trap instead of shallow trap. Okay. All right. So now to better understand the concept that we have learned in this lecture note, let's solve a single example. But I guess we need to take a short break time. So let me stop here. Then in the next upcoming movie clip, I'm going to record the example.